Hey everyone, welcome. For this deep dive, we're looking at something, well, maybe unexpected.
Yeah, definitely sounds a bit strange at first blush.
Calculus, specifically differentiation and food safety, seems worlds apart.
But it's actually a really powerful link. We've got some notes here, basically looking at how bacteria grow in meat.
Okay, bacterial growth. I'm with you there.
And how understanding differentiation, that math concept about rates of change, is actually key to keeping our food safe.
Right. Okay, so rate of change, like finding the slope of a line on a graph, that kind of thing.
Exactly that. But here, the graph isn't just abstract numbers. It's plotting, say, bacterial population over time.
In something like meat. Okay.
Yeah. And while knowing the total number of bacteria is important, what's often more critical for safety is how fast that number is going up.
Ah, the speed. Are they just slowly increasing or is it like exploding?
Precisely. And how fast is the rate of change? That's where differentiation comes straight into play.
Okay, connect the dots for us. How does the math work here?
Well, our notes show that bacterial growth follows certain patterns, which we can model with mathematical functions. Let's call the population P at time t, so PB.
Leave it FT.
Got it.
Population size.
Right. But differentiation gives us the derivative, PT.
Yeah.
And PT, that tells us the instantaneous rate of growth, the speed at that exact moment.
So PT is the crucial bit, not just the total PT.
Absolutely. Think about the phases of bacterial growth. There's often a lag phase, things are slow, then boom, an exponential phase, sometimes called the log phase. That's when they multiply fastest.
The dangerous part.
The most dangerous part. And understanding the derivative, P, helps scientists spot that rapid acceleration, that log phase, much earlier.
So even if PT, the actual number, seems okay right now.
Exactly. If PT, the rate, is high and increasing, you know you're heading towards trouble fast. It's like knowing your speed and acceleration, not just your position.
That makes sense. It gives you predictive power.
That's the key takeaway from these notes. Predictive power. If you know the current count and how fast it's increasing the derivative, you can project forward.
And that lets you do what? Set expiry dates?
Yes, things like shelf life, safe storage temperatures, because temperature massively impacts PT, the growth rate.
Ah, right. Heat or cold slows it down.
Or speeds it up.
Yeah.
It also helps design processing methods. It's about being proactive, not just reacting when counts are already too high.
Wow. So differentiation isn't just some abstract thing you learn in math class.
Not at all. It's a practical tool, a really vital one for analyzing and predicting how quickly food might become unsafe.
It's kind of mind-blowing, actually. This math is working behind the scenes to keep us safe.
It really is. Understanding that rate of change is fundamental to managing risk in so many areas. Food safety is just one powerful example.
So wrapping this up, this deep dive definitely shows calculus isn't just theoretical.
Nope. It's applied science, underpinning modern food safety protocols, driven by calculus.
It really makes you wonder, doesn't it? Where else is this math of rate of change quietly working, keeping things safe or efficient, without us even noticing?
That's a great question. Maybe in transport systems, public health tracking, financial markets.
Yeah, maybe. What other everyday things could we understand better just by looking not at the how much, but the how fast?
Something to think about, definitely.
Yeah.
Lots of hidden calculus out there.